Welcome to this video. In this video we're going to discuss complex functions. Now, a discussion of complex functions is the foundation point for a discussion of a branch of mathematics known as complex analysis. Now, what is complex analysis? Well, complex analysis is very analogous to real analysis. In real analysis, you study real functions, which are functions from a real variable to a real number. And we study incredible properties of some of these real functions, such as continuity, differentiability, even integration. Now, complex analysis, we study complex functions, and these are functions from a complex variable to a complex number. And amazingly, the same concepts as we had in real analysis, such as continuity, differentiability, even integration, they come across from real analysis into complex analysis, and they are just as beautiful as they were in real analysis and in calculus in complex analysis. In fact, in some ways, they are even more incredible, as we will see later. However, to start a discussion of this incredible branch of mathematics called complex analysis, we need to first discuss complex functions and get some understanding of what this actually means. So firstly, let's just write down, just to remind ourselves, what a real function was. So a real function was a mapping, which we often call f, which was a mapping from the set of real numbers to the set of real numbers. So remember, the set of real numbers, fundamentally that is just a set with a huge number of symbols in it, and these symbols have got incredible algebraic properties defined on them. So we have an addition defined on this set, and we have a multiplication defined on this set to make it a field algebra. So it's got an incredible algebraic property. It's also then given a topological property, so we define which elements of the set are next to each other, if you like. Remember, that's what topology is all about. It's about taking a set with arbitrary elements in and then defining which elements are going to be next to one another. And that gives us then this intuitive picture of what this set actually represents, which is the one-dimensional continuum. So remember, we often think about ascribing every element of this set of real numbers onto the one-dimensional continuum, and then this one-dimensional continuum has the same topological structure as this abstract set up here, i.e. if the 2 points are next to each other in speech marks, in the set, in the topological structure on the set, they are next to each other on the one-dimensional continuum. Remember, of course, topology is more complicated than that. The actual way of defining how things are next to each other when you've got infinite number of elements becomes very complicated. You do it by defining the open sets, but fundamentally that's what that abstract concept is capturing, the idea of what is next to what. How fundamentally it's geometrically organized. Although, of course, there's a stronger notion in geometry, this notion of the connection and the notion of a metric. Topology is a fundamental part of geometry, and it defines simply what is next to each other, what is connected to what. The real numbers, an incredible structure that we've defined, and then real functions, quite simply, they take every element of this set and then they ascribe it to another element of the set. So if you wanted to draw a picture, we could draw two one-dimensional lines, like so, and then the function quite simply takes every element, and we could just label an abstract element x, and then it maps it onto another element on the real numbers, like so. So this arrow represents the function, and here is the answer, which we denote f of x. So for instance, if we wanted a really simple example, we could take the function f maps x onto x plus 1, and all that would do is it would map every element of the real number onto the number 1 above it. So it would map 1 onto 2, 2 onto 3, it would move everything along to the right on this picture by 1. So With that in mind, let's now define what a complex function is. So a complex function, quite simply, it's going to be a mapping from the set of complex numbers to the set of complex numbers. Now remember, just as we've just discussed the real numbers and we've broken it down into what this abstractly is, this is just the same. This is just as credible. You might not have as much intuition for the complex numbers as you do for the real numbers, but it's just as credible a mathematical structure as this. Remember, this is fundamentally just a set, and we could write it down like so. So this is the set of all elements, all symbols, if you like, because that's all they fundamentally are. Some humans sat down and created a great big list of symbols, effectively. All the symbols of the form a plus bi, where a and b are both elements of the real numbers. So of course the entire set of real numbers is contained within the set of complex numbers, because when you set b equal to 0, which you are absolutely in your right to do, then a can vary over the entire set of real numbers, so they're all contained within that. And of course, we often think of the set of complex numbers as being like the plane, the complex plane as we call it. So along here, we think of this line as being the set of all real numbers, and then as you go out into these parts, then they've got an imaginary component as well. And every single real number, you can fix the real number component here, and then you can vary b over the entire real numbers, so you end up with an entire line like so. And indeed, we often, and indeed for the purpose of complex analysis, we will give the set of complex numbers the topological structure equivalent to the two-dimensional plane. So we will have elements in this abstract set, and remember it is fundamentally just an abstract set of symbols. We'll have elements of this abstract set ascribed points on this plane, and where two points are next to each other, again in quote marks, on the plane here, they will be next to each other according to the abstract topological structure on this abstract set. And of course the bit that I missed out here when we went from discussing the set to discussing the topological structure is a discussion of the algebraic structure. We have defined on this a notion of addition, a notion of multiplication, and it obeys all the axioms of field theory. So this is a field algebraic structure just like this was a field algebraic structure. So algebraically they are just as valuable as one another, the real numbers and the complex numbers. In a way you could say that the complex numbers are even more incredible because they obey the fundamental theorem of algebra, which actually isn't really fundamental to algebra at all, but it is an incredible theorem about algebraic properties within this set. So in a way you could say that this is even more incredible. It's just we haven't been taught it from as young an age as we were taught the real numbers, and therefore have less intuition for what this means. But fundamentally it's a very credible structure, the complex numbers, and we are now defining functions from a complex variable to a complex variable. And all this is going to be, analogous to what we drew before for the real functions, is a mapping f that takes any point in the set of complex numbers, any element, and we often don't use x anymore. To show that we're doing complex analysis, we use z instead as our variable. And then it's going to map it, this is the function here, to an element in our codomain here. The codomain obviously being the thing that the function, the set that the function maps the domain from, and I will just go over that terminology for anyone who's not familiar. When we discuss functions from one set to another set, we use the word domain to mean the set that we're mapping from, and we use codomain to mean the set that we're mapping to. So we can say that any element of the domain here, which is the complex numbers, is mapped onto an element of the codomain, which also is the complex numbers when we're discussing complex functions, and we'll call that f of z. So this is quite simply what a complex function is. It's really not complicated. It's just analogous to real functions. We are going to take all elements of the complex numbers and we're going to map it onto another complex number, like so. So let's do some examples to get this nailed in. So again, let's start with the really simple ones. So we could say that we're going to define our function so that f of z is going to be z plus 1. Really simple. what is that going to do? We can even visualize this now if we keep it that simple. So we've got all elements of here, and we're going to map them using this function. Well, of course, remember, this was representing the real axis of the complex plane. So if we're going to add 1, all that's going to do is it's going to move every complex number along in the horizontal direction to the right by 1. So this element here, it wouldn't be mapped to what we've got on the picture here. It would be mapped to something like this over here on our picture. So it was here, it will be moved to the left by 1. And indeed, every single element on here will be mapped onto a point in the codomain here that is just 1 to the left of it. So that's really simple. We can nicely visualize what that's doing. We could even, if you want to visualize this in your head, all you simply need to do is imagine loads of arrows going like so. So that would be that point. If we're going to take this point, it would be going like that. So every single point in here is going to have an arrow taking it to a point over here, and that point is just going to be 1 to the left, sorry, to the right of it on the complex plane. So let's do the other obvious example, which is f of z equals z plus I this time. So of course, the imaginary axis of the complex plane is this one in our picture. So by adding I, you're going to move upwards this time by 1. So this point here will be mapped onto the point 1 above it, like so. So over here it will be mapped to somewhere like this. So you can just imagine taking every element on this plane, just moving them all together up by 1, and that's what they'd be mapped onto in the codomain over here. So that's some really simple examples. Let's go a little bit more complicated. So what about f of z is equal to z squared? That's a good example. And indeed we'll stop with this example at the end. So what is this going to do? This is more complicated to understand, but it's really important to do this as an example because it shows you that the basic concept of polynomials that you had in real functions actually comes across really simply into the world of complex functions. So let's just think about this. So let's take a point on our complex plane and actually compute it. So let's take this point and let's say that that is 2 plus I. So that point there. And let's think, where would this be mapped onto by our function if our function is z squared? Well, it's just going to be mapped onto 2 plus I squared. How do you square a complex number? Well, you use the distributivity law. So you can rewrite 2 plus I squared as 2 plus I times 2 plus I. And then you can use the, in this case, left distributivity law and rewrite this as 2 plus I times 2 plus 2 plus I times I. And then you can use, in this case, the right distributivity law to rewrite that as 2 times 2, which is 4, plus 2 times I, which is 2I, plus 2I plus I squared, which is minus 1. And that, of course, comes out as 3 plus 4I. Now, just plotting that on our complex plane, which is the codomain up here, 3 plus 4I would be somewhere up here. So that can represent 3 plus 4I. And therefore, this point 2 plus I, using this mapping f of z is z squared, is going to be mapped up to there. Now, of course, that's just one point. Let's think about what the function looks like more generally. Well, it's helpful then to remember that complex numbers can be thought of also in their modular argument form. So remember, the modulus of the complex number is a real number that is the distance, a positive real number, from the 0 point of the complex plane to the element. So that's the modulus of the complex number. And the argument is then the angle from the real positive numbers within the complex plane to the line connecting the point that is the complex number to the element 0. So that's the argument of the complex number. And remember, why is it useful to think in terms of modulus and arguments of complex numbers? Well, we know from basic properties of complex numbers that when you multiply two complex numbers together, the complex number that you get at the end will have argument equal to the arguments of the two starting complex numbers added together, and modulus equal to the two moduli of the starting complex numbers multiplied together. Therefore, if we're squaring a complex number, then the answer is going to have modulus z squared, and it's going to have argument twice the argument of the original complex number, and that's helpful in terms of intuition for what this function looks like. So, let's firstly think about where the positive real part of the complex plane would be mapped onto. So all of these elements, they have argument 0, so their argument after being squared will also be 0, and of course that's plain common sense, because we know that when you square a real number, it's not suddenly going to become negative, and it's not suddenly going to get an imaginary component, it's going to go to another real number. So that's good. And then, of course, quite simply, the modulus is going to square. So that's really obvious. So all of these numbers are quite simply going to be moved up a little bit, or potentially down a little bit if we're talking about points. 0.5, for instance, will go to 0.25. But the point is they're going to go to other numbers on the positive real part. They're just going to be stretched out. If they're above 1, they're going to be stretched upwards. If they're below 1, they're going to be stretched downwards towards 0. Okay, so this part is going to be mapped onto this part. That's quite simple. Then thinking about all the parts that actually aren't positive real numbers, so all the parts with imaginary bits and with negative, the negative reals here, well, their argument isn't equal to 0, so their argument is going to double. So effectively what's going to happen is they're all going to be twisted around. So they're going to double their argument. So you can imagine taking the entire complex plane and then twisting it around in this anti-clockwise way, so that all of the points are going to be carried to a point that is twice the argument that they originally had. And of course, points down here where the argument was very large, so just drawing this on. So if we had a point down here, its argument, of course, is all the way from here right round to here. Then if we double that, we're going to take it right back round. So it's going to end up coming round again, of course. But that doesn't matter. All of the points up here in the upper quadrants, their argument is of course less than 180 degrees, and therefore when they have their argument doubled, they're going to be carried, they're not going to cross twice, they're not going to double back on themselves. The points over here are going to end up down here, points here are going to end up here. My point is that they're not going to, when they're doubled, they're going to be less than 360 degrees. So if you think, all of these are going to end up being stretched round so that they fill the entire 4 quadrants, and then the points down here, because they've got very large arguments, they're going to be doubled, and therefore they're going to go all the way back round so that they cross this line again, and then they're going to be stretched out so that they span all of the 4 quadrants again. So each of these, the top half and the bottom half, is going to be stretched and warped by this tornado function, if you like, twisted in this way, anti-clockwise, and both of them are going to end up spanning in the codomain the entire complex plane, well, nearly the entire complex plane, all 4 quadrants. Of course, 0 here won't, it will just be mapped onto itself. So it won't be covered twice in the codomain, but other points will have both a point in the upper 2 quadrants and a point in the lower quadrant that are being mapped onto it. And of course we know from basic understanding of complex numbers that I'm sure all the viewers have, that there are 2 answers. When you're asking z squared is equal to a complex number, there are 2 complex numbers usually that could be mapped onto that value. When they're squared, there are 2 solutions to the square root of a complex number. Okay, so we talked about arguments, let's just talk about modulus here. Of course, the modulus is going to be squared, so of course if the modulus is above 1, that means it's going to get bigger. If the modulus is below 1, that means it's going to get smaller. So again, we're stretching and warping the complex numbers up moduli, as well as twisting their arguments. So if the modulus is above 1, it's being stretched outwards. If it's below 1, and we can imagine that this ring that I've drawn here is the ring of modulus 1, if it's below 1 inside here, it's going to be stretched downwards. So it's this very strange function that, if you want to visualize it, is stretching the moduli either inwards if it's below 1 or outwards if it's above 1. Meanwhile, it's also twisting round in this anti-clockwise way. So that's what you can actually sort of visualize if you're thinking about how to actually visualize these this function, f of z is equal to z squared. And remember, 0 is being mapped onto itself, so that's nice and easy. That point, at least, is staying the same. The positive real numbers, they're just being stretched out along this line. They're not going to... They're the stable point, if you like, for this twisting, spaghetti kind of anti-clockwise motion that the rest are going through. But they're laddered here, they're stable, whilst the rest is all twisting round in that anti-clockwise way. Okay, so I will end the video here. I hope that that has hopefully convinced you that these functions, complex functions, they are at the very least just as valid mathematically as real functions. You might not yet completely understand what is the point of studying these things. Why would I want to build a function from complex numbers to complex numbers? However, they do become important in many more advanced parts of physics, such as quantum mechanics, for instance. Functions that give complex values are very, very important in quantum mechanics. It's not quite true to say that the functions in quantum mechanics are complex functions, because usually the variable there is three-dimensional real space rather than the complex plane, but certainly the values are complex numbers in wave functions in quantum mechanics. However, remember that this is pure maths, and mathematicians are allowed to study abstract concepts without necessarily knowing whether these are going to have any real-world applications when they're doing that. And hopefully I've convinced you that this is just as valid mathematically as this, even though you may have more intuition for this. But hopefully by giving you some of these examples, I have shown you that even these more complicated functions, they can still have a visual interpretation, and it's nice when you go to more advanced parts of maths and you can still visually interpret them, because it's certainly as you get higher and higher up in maths, it gets to a point where you can no longer, the human brain is no longer capable of visualizing these abstract concepts, and they truly are just abstract concepts. Thank you.